our electrostatics, and then we will go to the magnetostatics. Okay, so let me share the screen with you. Okay, so it's here. Yes, before going to the lecture, just to share with you guys, your assignment 2 is ready. So please go ahead and solve the 5 problems of assignment 2. And as I have told you, assignments are, the questions in the assignments are very similar to how we ask in the exams. Okay, exams and other assessments.
Doctor?
Yes.
Assignment 2, what is about? Is it the same material as the quiz?
Assignment 2, I don't remember.
If it is not the same material, could you may just postpone it till Sunday, the next week?
Assignment 2.
One of them, Doctor, the quiz or the assignment?
Yes, the quiz or the assignment, one of them.
I agree, Doctor. Having both at the same day is very hard.
Yeah, I think yes, it includes the quiz material.
So, Doctor, please, the quiz, make it on Sunday.
I think it makes sense because if we solve the assignment and we know our mistakes, we can be ready for the quiz.
Yes, and we saw the solution of the assignment.
Yeah, Doctor,
okay, what do you say, all the other students?
Same, Doctor.
Agree.
Okay.
All agree.
Good idea.
Everyone is okay, or if someone has a concern, please send me a private chat right now, because I have, when I change the date, it should be, everyone's, agreement. Okay, so I have few students who doesn't agree to postpone the quiz. In this case, what we can do? So do you think if I make the assignment to Wednesday, do you think it is fine?
No,
Wait,
no.
you have to on Wednesday. No, just make it on Thursday.
Okay, so I'm sorry guys, because I think we have it's difficult to agree on the postponement, because some of the students, they don't prefer, maybe they have their own obligations, why they don't prefer.
The majority, Doctor.
See, the thing is, Thabit, when an announcement is made, I cannot go with the majority. Because everyone has to agree. Otherwise, I will be getting emails, personal emails from the students saying that, you after doing that, please don't change. Every student has their own other different class schedule and other things. So, whenever I change, it should be agreement on all, agreement with all, not just with the majority. Okay, so try to understand that. Okay, in this case, I can't do much. So I have left with only one option to prepone the assignment. But since you are not agreeing to that, then let's just, keep it as it is.
Okay, Doctor.
Yes.
There is a question in the assignments outside from the quiz sections.
No, because the quiz is from lecture 5 to 8. I think there are a couple of questions in the assignment from that material. Not all,
Okay.
but a couple of them.
Okay, Doctor, since
Doctor.
is
Doctor.
due on Thursday
Just a
midnight,
second.
is it
Yes,
possible
yes.
to push it to Sunday?
Go ahead, Ibrahim. Say it again, once again, please.
Since the assignment is due on Thursday midnight,
Mhm.
is it possible to move it to Sunday?
Assignment, it's okay for me. If you want, I can postpone the assignment. That
It
should.
will be helpful so much, Doctor. Since the due is Thursday midnight.
Yeah, it's okay. I can make it till Sunday. There shouldn't be any issue. Okay, at least I can do this. And for this, I do not require any
Doctor.
approval because we are postponing the assignment. Yes.
Doctor, can I add a comment about quiz?
Yes, Michelle, go ahead.
Yes, I see. Whoever ready on the Thursday will be ready on the Sunday, and the quiz will be not outside the class time. So I don't think it's.
Yeah, you can. Your comment, Michelle, is okay. I can understand that. But maybe those students who are not agreeing on Thursday, maybe they are also trying to finish their assignment by Thursday. It's okay, because if the Sunday is the deadline for the submission, that shouldn't affect them. Okay, so let's keep it or just a second.
Doctor, I think it's fair to vote on this one.
Just a second. Okay, so guys, let's not waste time. Let's start our class. And regarding the quiz, let's see. I will think about it and I will get back to you. Okay, and also the assignment. But in the meanwhile, you just go ahead and start preparing. Okay. Okay, guys. Then I think the students who raised concern, now they are okay. Class, good. Thank you very much, guys. Thank you very much. Okay, then we will have our quiz on Sunday. Done?
Thank you, Doctor. Thank you.
Thank you so much.
So we will have our quiz on Sunday.
We appreciate it.
But the assignment will be on Thursday, because on Friday I can post the solution for you. Okay. So let's come back to our class. So assignment 2 is done. Yes. So before starting the class, there is one thing, guys, which I wanted to share with you. Please go and look at the assignment 1, the mistakes that you have done. And if there is any confusion or if there's anything that you did not understand, you can contact me, or you can show up during the office hours, or you can send an email to me, and then I will try to help, because there are some students who are really going through these assignments and notes, and whenever they have any doubts, they are sending an email to me, and I'm trying my best to reply as early as possible. So one thing which I wanted to share with you is a very general mistake which almost all students did. So that's why I'm showing that to you. Now, if you see this homework, this is the homework 1 solution. Now, in the homework 1 solution, there is a problem, and my one of the assignment 1 problem was very similar. So if that, so this one, so see, this is the ring. So this is the example of our textbook whose solution is in our homework 1. So we are trying to find the electric field at this point P 004 because of this ring, and this ring is carrying a uniform charge density of this value. So you can go through the derivation, how the derivation is done in a very similar way as we have done it for other cases. But there is one thing which I want to highlight here. See, we are using the same general expression here, which is rho L dl over 4 pi epsilon naught r cube times r bar, which is our distance vector. And the distance vector, we got it. And then we put it in the integral. Now comes the most important point. When I put it in the integral, now I see that my electric field has 2 components, a rho component and a z component. So now I'm separating both these components. So therefore, my electric field here, okay, let me zoom it. My electric field here has an a rho component and a z component. See here, these 2 components, and they are inside the integral. Now, can I remove this unit vector a rho outside the integral? And can I remove the unit vector az outside the integral and do the integration? You have to think about this, because if you remember in the first class when I spent time on the coordinate systems, I told you, see here, it is the unit vector a rho, but the integration is with respect to phi, d phi. So you have to be careful. You have to first identify, is my unit vector a rho is a function of phi or not? Because if it is a constant, if it is not a function of phi, then you can take it out. Otherwise, you cannot. This is not like our Cartesian coordinates where ax, ay, and az, they are all independent of the other space variables. But here it's not the case. Now, how do you identify whether a rho, unit vector a rho is a function of phi or not? Go and look at the unit vector transformations. And if you will see that a rho, if I want to write it in Cartesian coordinates, a rho is becoming cos phi ax plus sine phi ay. And this is telling us that your a rho is a function of phi, because as my phi angle is changing, the a rho direction is changing in the cylindrical coordinates. So therefore, especially when you are working with cylindrical and spherical coordinates, when you are working with a rho and whether you are working with a phi, and when you are doing the integrations, please be careful. Okay, so that means it is a function of phi. I cannot take this outside the integral. Now, how to solve this? So the best way to solve this is change your unit vector of your cylindrical coordinates a rho in and write it in terms of the Cartesian coordinates, and then you complete your integration. This is the way that we need to follow. Now, what about AZ? Can you take AZ outside? Yes, because AZ is not a function of, see here. See here. I'm taking AZ outside the integral. Why? Because AZ is not a function of phi. How can you think about it in the cylindrical coordinates? You know, just move AZ anywhere in your space. If you move AZ, always AZ will point upwards. And if you go and look into the transformations, the AZ in cylindrical coordinates is same as the AZ in Cartesian coordinates. So therefore it is independent of phi. And that's why I can take AZ outside and I'm saying 0 to 2 pi integral of d phi. But here I cannot take arrow outside. So to solve this, you have to convert it into Cartesian coordinates and replace your arrow with that equivalent unit vectors in Cartesian coordinates and then do the integration. So in this case, it will be cos phi ax plus sin phi ay d phi. And you do this integration. So this will be cos phi d phi, this will be sin phi d phi and its results, and then you have to get the answer. Of course, if you go and if you look at it, in the end, because you have now converted your unit vector arrow to the Cartesian coordinate ax and ay, then your electric field vector in the end will be in terms of Cartesian coordinates, because it will be in terms of ax, ay. No problem. Once you get the electric field in terms of ax, ay, and az, which is in the Cartesian coordinates, convert that vector into the cylindrical coordinates. But if it is asked in the problem, if it is not asked, you can leave it like that. So this is very, very important. This is a key. So therefore, you should not do that. And this kind of example is done in the homework one, the first homework. Similar problem, I gave it in the assignment. See? This is the similar problem which was given in the assignment. And if you see here, this is a non-uniform charge density. It's a non-uniform charge density. So you cannot take out rho L outside. And if you cannot take out rho L outside, you are ending up with this one, which is 0 to 2 pi sin phi d phi arrow. Now you cannot take this arrow outside because this is an integral with respect to d phi. Sin phi is there, leave it, but d phi. So therefore you have to convert arrow to cos phi ax plus sin phi. This is what I have written here. And now you go ahead and do the integrations, and then you will end up with this expression. And again, as I told you, my electric field is in the Cartesian coordinates now. It is no longer in the cylindrical coordinates, because we started with cylindrical coordinates, but we did the unit vector transformation in the middle in order to do the integration. And because of that, we ended up with an electric field in the Cartesian coordinates. But no problem. Anytime you can convert this electric field vector, which is in Cartesian coordinate, back to the cylindrical coordinates. And these examples you guys already did in the problem sessions 1, 2, and 3 in your lab. But if it is asked, so this is what I wanted to emphasize. So please be careful, especially when you have arrow in Cartesian, in cylindrical coordinates, and when you have AR in spherical coordinates. Because these are the two unit vectors which you will come across, a lot of time during this course. So whenever you do the integration, please be careful. Done? Anything else you want to ask? Okay, so now let's go back to our lecture. So let's quickly wrap up our lecture. So if you remember, in the last class, we started with the Laplace and the Poisson's equation, and we looked at both of them, and we found that you can apply Laplace equation when you have a charge-free region, and you can apply Poisson's equation when you have a region where you find charges. And at least for our course, we don't deal with Poisson's equation. It is more difficult to solve. So we would deal with Laplace equation, and mostly for our capacitors, because we are dealing with mostly two conductor capacitors. So the equation will be the Laplace equation, because we will find the electric field. Sorry, we will solve the Laplace equation in this dielectric material where there are no charges. That's why. So we did it for the parallel plate capacitor, And then we also did how we can get the capacitance from this potential expression. We all did that. And then we stopped here for a spherical capacitor. Now, in the spherical capacitor, if you see here, you have the outer conductor, VB, and the inner conductor, VA. So inner conductor, higher potential, placed at VA. Outer conductor, lower potential, placed at VB. So the potential difference is VA minus VB. Now, how would be the electric field for this one? The electric field will go from the positive charge to the negative charge. So all these blue arrows is a kind of electric field. And what will be the direction of this electric field? Because now this is a spherical capacitor. So how do you think about a spherical capacitor? Think as your soccer ball, and the surface of your soccer ball is your outer conductor. And inside you have a dielectric material. And again, at the center, you have another solid ball, which is made up of a metal. And that solid ball is your inner conductor. And the surrounding medium, as I told you, we assumed it as a dielectric with material epsilon. So how would be the field? The field will be going from the positive to the negative, and it will be radial. Radial means it will be in the R direction if you look at the spherical coordinates. So how do you solve? You have to use the Laplace equation. And in the Laplace equation, we are solving the Laplace equation only in this region. So that's why it is between A and B. What is A? The inner conductor radius. B is the outer conductor radius. So we are in this region. Now the Laplace equation in spherical coordinates is this one. But from here, we are saying that this is going to 0 and this is going to 0. Now why we are saying these two are going to 0? I have explained this in the last class. Yes, Mr. Abdullah Ali, can you tell me?
Because the electric field is in the R direction only.
Exactly, because the electric field is in the R direction only. Very good. So to solve Laplace equation, as I told in the last class, we need some experience, we need some knowledge. So, and that knowledge is coming from the electric field. And we are seeing that the electric field is only going in this direction from here to here. And in spherical coordinate, this direction is R. So therefore, my electric field has only a component in the direction of R. And that too, if the electric field is only moving in this direction, that means this component ER is also a function of only R. So this is the prior knowledge that we need to solve the Laplace equation. And because this electric field have only the R term, it is only in the AR direction and it's a function of R. From here, we can conclude that the potential will also be a function of only R. And I showed an example to you where I showed you that if the potential is a function of R, only R, then your electric field will have only R component. And I was also trying to find a problem, an example from our textbook to show you another example, right? So I found that example and then I'll just share it with you. So this is the example which I was looking for, this one. See, here, if the potential is a function of R, theta, and phi, all the three, then your electric field, sorry, where is the, then if you see here, your electric field will have all the components AR, A phi, and A theta. But if your electric field has only one component, and that too, the component is a function of only one spatial coordinate, then your potential will also be the function of that spatial coordinate. Okay, so that's the reason we are now removing these two. So let me make it small so that I can annotate on this. So this goes to 0, this goes to 0, and only this is left. So integrate it one time. So this r square is gone because r square taking on the right hand side will become 0. So this is our differential equation that we need to solve. So integrating once, this will be gone. So r square dou v over dou r is equal to the constant C1. Then integrate this second time, then you will get v of r is equal to, what will be the C1? It will be minus C1 r to the power of minus 1. Thus the second constant, C2. Okay, so remember this one. This is dou v over dou r is equal to C1 over r square. So the integral of 1 over r square is this one, minus r to the power of minus 1. And then the second constant. Now we got this potential expression. So the only thing left is to find this constant C1 and C2. Now, how do we find the constant C1 and C2? Again, with the boundary conditions. We know that the potential here, if this is A, see, this is A. So this is just above A. So I can say it as A plus. So here the potential should be equal to VA. First, see, this should be equal to VA. R is equal to A. Then this is the second one. Here, what is this distance? B. And just before the conductor, I can say that it is B minus. And this value is, the potential should be, this potential, this expression should be equal to VA at R is equal to A. And this expression should be VB at R is equal to B. So at R is equal to A, if you substitute at R is equal to A, this must be equal to VA. And at R is equal to B, this must be equal to V. And then we know our potential difference V0 is VA minus VB. So this will be C1P to the power minus 1 minus C1A to the power minus 1, or it is C1 times 1 over B minus 1 over A. Now, our objective is to find C1 and C2, right? Now, we have two equations and two unknowns. So this is two equations and two unknowns, C1 and C2. In solve as you like. So I'm showing one solution here. So I'm writing V0, which is the potential difference. Then I got this, and therefore my C1 is V0 over 1 over B minus 1 over A. And if I substitute in any one equation, I can get VB. I can get C2, which is this one. And I got C1 and C2. So substitute back in this equation. This is your VR. So this is the expression of VR, which is valid in the dielectric region between the two conductors of our spherical capacitors. And if you want, you can cross-check this equation. I also told you, how do you cross-check that? How do you cross-check your boundary conditions, these two boundary conditions, this one and this one should satisfy. So you can put it here and check. So this is the potential expression. So one simplifies, this is the value. V0 over 1 minus B over A times 1 minus B over R plus V. And if you can cross check this, when you put R is equal to A here, it will reduce to VA value. And when R is equal to B, it will reduce to VB value. That means it's correct. So this is our potential. So we got the potential. Now what you need to do? Electric field, right? So this is my potential V of R. Then electric field. So electric field E is minus del V. So in this spherical coordinates, so this is the del operator in spherical coordinates. So you define the partial derivative of this with respect to R, and then you will get the electric field. And the electric field is this. And as we have already, we have got the prior knowledge that our electric field will have only AR term, and it will be a function of R. So this is the electric. Okay, so this is how you can solve Laplace equation in the region between the two conductors to find the potential. Then from there you can find the electric field. Then if you want to apply the boundary condition between the conductor and the dielectric, you can get the charge, and then you can find the capacitance. And we did it for one example here, but as I told you, we will not do for all examples. So this is for the spherical capacitor. You have one more example here. This is for two sheets. Okay, this is for two sheets, and I'm seeing the top view of the two sheets. So this is the top view. So the sheets are something like this. They are placed at an angle. So this is one sheet and this is another sheet, something like this. And this is the region between them. And remember, these sheets, they are not joined. See, there is a small gap here. Now, how do you do this? We will not go through the complete analysis, but we will just try to visualize how the electric field will be and what will be the function of electric field. Only these two things. Now, so this is one plate. This is another plate. This plate is kept at a potential of V0, and this plate is kept at a potential of 0 volts. And the angle between them is 60 degrees. And the region here is, I think, air, if I'm not mistaken. The region here is air. So what is the potential expression in this region? So how would be the electric field here? So we know that this is at the positive charge and this is negative charge. So therefore, my electric field will be going from positive and then it will be reaching negative like this. So which coordinate system would be the best coordinate system to to solve? See, it is going in this direction. So which coordinate system will be the best one?
Cylindrical.
It is cylindrical. Cylindrical. So what I can do, I can make this as the z-axis. So I'm seeing the top view. So if I make this as the z-axis, then what will be this variable? This variable will become your, yes?
Phi.
Phi. This variable will become your phi. So now what we can do is we can now visualize and we can say that since my electric field E has only phi, is a function of only phi, because this is phi. Remember in the cylindrical coordinates, x, y, z. So this is x, y, and this is z. So my one sheet is here. This is my one sheet. Sorry guys, drawing. Okay, so my one sheet is here. Okay, at 0, and my another sheet is somewhere here. And this angle is, so my electric field, how the electric field is? The electric field is in, so this is at lower potential, this is at higher potential. Am I right? Yes. So my electric field is in like this. So it's a function of phi. And not only that, since it is moving in this direction, it will be just E5 will also be just a function of phi. So if this is what we got, then we can conclude that my potential is also a function of phi. So therefore, if you write the Laplace equation here, then you will see that with respect to d rho, with respect to dz, and only one is left is phi. And you just solve this. Okay? So once you solve, you will get the answer. So now this problem, I am leaving it to you. So you can go ahead and you can look at your home. So I explained the main idea, and you can go and look at the solution. Okay? And in fact, similar type of problem. Yeah, Mr. Abdul Majid, yes, there was a small, time span of maybe 10 seconds where the internet was unstable. So that's why at that time, I stopped talking. Okay, now you can hear. Yes. So this example, you can do it. Yes. This example, you do it at home. So this is the Laplace equation. So where we looked at 2-3 examples of how do we solve the Laplace equation. And this actually concludes our chapter 6 and also the electrostatics. And remember guys, there are several examples in our homeworks for this Laplace and also in the textbook. There are many examples. So I encourage you, please go and solve these examples so that you will get, more, you will get more used to, tackling, different kinds of capacitors and other things. So if you see here, see, this is the exact example which I just not showed you. See how to solve this. It's here. See, then this one, cones. So you have two cones. One is a small cone, another is a bigger cone. And we want to find the electric field between the region separating these cones. So here you need to use spherical coordinates and solve it. So how to solve it? It is explaining it to you. So go and try to look at these examples. Okay, then I think no, this one, not this one. Yeah. So this is an example where you can see instead of your Laplace equation becoming a function of only one spatial variable, we have seen only one spatial variables. In parallel capacitors, it was X. In spherical capacitor, it was only R. And in this two plates, we have seen that it was only phi. So that's why our solution became very simple. This is an example where in the Cartesian coordinate, the region between the two capacitors is no longer a function of one space. It is a function of two spatial variables. See, it's a function of two spatial variables. Because one plate is like this and another plate is like this. Let me make it wrong. One plate is like this from here to here and another plate is like this. Like this. So therefore here it is now a function of two variables. Now solving this, you have to go and borrow your experience that you got in your mathematics. How do you solve differential equations of different types? And then from here, you have to get the answer. And this example gives you, how to get that example. And it's not so straightforward because when this happens, your differential equation has become complicated. So therefore, your solution becomes complicated. And usually, how do we tackle these kind of problems? Rather than going for a closed form solution, we try to tackle this problem using numerical techniques. Numerical techniques. And this is your experiment number 3. And experiment number 3, you will learn how we can tackle these kind of problems without going to solve it with your hands and get a closed form answers. We just solve it in a numerical way. We use numerical techniques and we can solve it because that becomes much easier. Okay. Well, just to let you know, this kind of 2 variable dependency of your potential, we will not ask such kind of problems in our exams or in our assessments. Okay. But this is just for your, information so that you can look at it and understand. Done. So this is our experiment number 6. See, you also have some examples of solving it for this kind of 2 conductors. See, it's also here. So please go and try to look at these different examples. Okay. So this is the spherical capacitor. Yeah, I think this is a spherical capacitor, 2 spherical shells. So you can go and look at them also. So this actually concludes our experiment number, our chapter number 6. Chapter number 6. Okay. Remember, the method of images are not included in our syllabus. So now let's go to our chapter number 7. That means we will start with the magnetostatics. So till now, we were dealing with static charges. We were dealing with static charges. That means the charges which are not moving. And that's why these charges which are not moving, we saw that those are responsible for the electric flux density or the electric field. And this is because of the force between them and coming from the Coulomb's law. And then we also saw that from the flux density, there exists an electrostatic potential, which we have seen all, and also the boundary conditions. Now, from this chapter onwards, we are looking into moving charges. That means what will happen if we now allow the charges to move? Then, in this case, you will get magnetic fields. So H is called as magnetic field, which is, analogous to the electrostatic field E, and you will get the magnetic flux density B, which is analogous to the electrical flux density D. So we will get this. Now, when you move charges, then you will see that you will get 2 cases. And this is what I'm summarizing here. So this was our first case where our chapter 4, 5, 6 was there, where we had the static charges and we saw point charge, line charge, volume charge, surface charge. So only electrostatic field was produced and there was no magnetic field. Now, if we allow the charges to move, which is our case 2, then your magnetic field will not be equal to 0. That means your magnetic field will exist. And your electrostatic field, your electric field, I will not say electrostatic, your electric field, it may not be 0 or it may be 0. It may not be 0, it may be 0. It depends on how you are moving these charges. And from there comes the 2 cases, which is case 2A and case 2B. See here? So you have the case 2A and case 2B. So what is case 2A? So case 2A is when you have a DC current. DC current. What that means, your charges are moving with the uniform velocity, or the drift velocity becomes uniform because your potential difference is fixed, and that potential difference allows a uniform velocity. So it's a DC current. So under this scenario, your electric field will be 0. That means your moving charges will not create any electric field. Only magnetic field will be created. And this kind of magnetic field is called as static magnetic field or magnetostatic field. So under DC current, we say it as magnetostatic. Okay, under DC. Now, if you use AC current, that means you are changing the potential difference between a conductor. So if this potential difference is changing, then your velocity of your carriers will also change. The drift velocity will vary. And this drift velocity, when it varies, then the magnetic field will be produced, and this magnetic field is now called as time-dependent magnetic field. And because of this time-dependent magnetic field, an electric field will also be produced. And this electric field is called as time-dependent. So here, your H will not be 0 and E also will not be 0. Here H will not be 0, but E will be equal to 0. And here it is called as time independent magnetic field. That's why it is called as magnetostatics. But here these are called as time dependent, because we are using an AC source. Or sometimes, sorry, not sometimes, we use the, instead of using time dependent, we use time varying. We use time varying. Okay, so this is our chapter 7, 8, and this part is our chapter 9, 10, if I'm not mistaken. Okay, so clear? So now let's go to our magnetostatics. So in our magnetostatics, remember the current, whenever we are talking about a current, we are referring to a DC current. We are referring it to a DC current. So we are referring it to a DC current. So again, so we can have different kinds of currents here. See, this is the most simplest one, which is the line current that is passing through a small, a negligible thickness or negligible cross-section line of wire. Then you can have a sheet current. That means the current flowing through a very thin sheet. Now, how do you find the current which is flowing through very thin sheet? It will require you to first know what is called as the current density. And here, the current density for a sheet current is defined as K bar, and it is in amperes per meter. So K bar can be flowing in any direction. So it can have different components. But here we are only concerned with the component which is perpendicular to this length L, because we want to find the current flowing in this direction. Okay, current flowing in this direction. So only we want the K component which is in this direction, that is normal to L. And that over this length L, that's over this length L will give me the current. And for the volume, we have already seen. The volume current is your conduction current. If this is J and if this is the cross-sectional surface, then J bar is called as the volume current density, amperes per meter square. And to find the current, it is J bar dot ds bar, which is nothing but the component of J, which is perpendicular to this S. Okay, so we will stop here and